Dear student, this is Professor Ashok Kumar, and you are watching me on our online video lecture platform, through which we are providing numbers of video lectures on different specific topics and subtopics. Uh, in today's video lecture, we are going to discuss very much important chapter, and that is beams and columns. Basically, this chapter comes in subject Fundamental of Machine Design in fourth semester degree mechanical engineering. So, this entire lecture will cover the basic introduction of beams and columns, its type, its specific features and application. Starting with an introduction of beam, we will start first beam. We will discuss over it, and once it is completed, then we will discuss on columns. So beam is a horizontal structure basically, and numbers of loads are acting perpendicular to the axis or the perpendicular to the axis of that beam is we term it as a beam. So in order to identify a beam, you just have to think that the kinds of loads which are acting, it must be actually acting on a perpendicular axis to the centroidal axis of beam. So whatever the loads which acts perpendicular to the centroidal axis of beam, or you can say that the longitudinal axis of the beam will be generally known as lateral load. Beam basically used for building and constructional work, some machinery, factory roof and sheds, where the beam finds its application. Generally, due to lateral load and some kind of moment, beam are always concerned with the shearing stress and bending stress, because we know that due to lateral load acting over the entire span of beam, there will be a chance to have the bending moment, which is responsible for the production, or we can say that the setup of bending stress. So, whereas different kinds of lateral loads are also acting over it, so definitely it creates a shearing stress over the entire span or some sections of that particular beams. Then look at the screen. We are now discussing about the different types of beam that currently being used for the various purposes. First and most important types of beam that you are looking in your screen, that is cantilever beam. Cantilever beam basically identified by its specific detail of construction. Look at the diagram carefully. One end of the cantilever is always free and other is fixed. This is specific identification of any cantilever beam. Due to only one support is provided over here and other end is free to move, this support is required robust construction. That means support should have the maximum strength in order to sustain all the forces acting in or over the span of the beam. So this is what the primary requirement of cantilever beam. If we are talking about the advantage of that particular beam, then we can say that it's very simple in construction, and thermal and ground movement can be easily sustained, because we know that movement or ground movement can be sustained easily sustained by this cantilever beam is due to that other end of this beam is free to move. So it allows some flexibility, allows some movement, linear movement, or as per the whatever the loads are acting, it allows some kind of flexibility. Due to large force and moment, it may possible that deflection and moments will produce having a large magnitude. This is why, because we all know that the other end of this beam is free, and if force is applying over here or entire span of the beam, then it may possible that the deflection due to large force deflection will be like that. So ultimately, we can say that there will be nothing to reaction at the other end because it is free. So large deflection will be possible to create over here. Similarly, due to large force, moment is also possible in large magnitude. So this is some disadvantages of particular, we can say that cantilever beam. In specific some application, big span is required. That means suppose the length of this particular cantilever beam is high, and you have to just use that particular length, uh, highly lengthen that beam, and so ultimately you require to have the some supportive structure mechanism, because we know that the other end is free, and if you have the cantilever beam which are very longer, it cannot resist the bending and shearing force. So in order to resist, in order to make a strong enough to resist that external load and stresses, we should to use a back span. Look at the diagram, below diagram, this one, this is back span in which one more support is provided, and over here, this is the portion of cantilever beam. So by using that back span, you can use cantilever beam in various application, highly loaded application where the loads and moments are acting on beam having the higher magnitude. So this is what about a cantilever beam. Next and most important types of beam are coming across, and that is simply supported beam. One can easily identify and explain what is the simply supported beam by looking the figure. Look at the top left hand side diagram. It's generally have the two support which are mounted on both of the ends, and both of the supports are roller support. Due to roller support, suppose you are applying force horizontally force over here, it allows the beam to move in horizontal direction, because there will be no resistance offered by this kind of the support, roller support, because it not resist any external movement or external force, movement due to external force. So this is the characteristic of roller support. If you are using simply supported beam and you are applying force in horizontal direction over here, beam will move in forward direction, because this is specifically roller support are used over here, and it will be never resist to external applied horizontal force. It will also move in the direction of force. So this is what the specific characteristic of roller support. One more thing that we should to discuss here is that if you are applying force in a simply supported beam like over here, or we can say that if you are applying force over here too, so bending moment of course will be acting over here, both of the end, and due to this lateral load, the section over here or any section you may select, it it it, it is subjected to little bit of shear force. So we can say that if simply supported beam is there, it may possible that both of the shear force stress as well bending moment will be set up. And advantage, if you are looking there, then it's very simple in structural detail. So this is what about we are discussing simply supported beam. Then after third types of beam, that is very similarly looking as that of the simply supported beam. But one difference is there, and the difference is that in place of two support that we are using in simply supported beam, here in case of continuous beam, there are more than two support are being used. So this is what the basic difference or constructional difference between continuous beam and simply supported beam. Then one more characteristic is that one support of that continuous beam is pin or hinge support. Look over here, and all other remaining support are roller support. So it clearly means that if you are now applying horizontally force, or either any of the end, then your beam will not move. Suppose you are applying force over here, so due to that force magnitude and its direction, beam will not move in forward direction. So it clearly means that it offers horizontal resistance in that particular point. Second and most important thing about continuous beam is that the bending moment is less and deflection is also less, as if we are comparing both of the terminology, bending moment and deflection, with simply supported beam. Third, most important advantage if you are looking for the continuous beam, then it is that it can be used for the large span. That means, look at the right hand side diagram. There is a bridge, and it is so longer. Its span is so longer. So in that particular case, specifically look at the bridge. There are 1, 2, and 3 support are being used. So it's clearly meant that in case of bridge and similar other types of constructional work, continuous beam finds its application. And if we are talking about disadvantages of that continuous beam, then this is that due to temperature or thermal stress, it may possible that it can contract or expand because it directly affected by the temperature. So this is what we have discussed about the continuous beam. Then after fourth type of beam is that overhanging beam. It's also very similar to simply supported beam, except a few things. Look at the diagram carefully. One end of that overhanging beam is beam supported, whereas other is roller supported. Exactly look like what we have discussed in continuous beam. But there is basic difference between continuous beam and overhanging beam, and that is that in case of continuous beam we are using more than two support, but in case of the overhanging beam there is only two support. One is pin and other is roller support. Second thing about the overhanging beam is that either on any kind of support, right side or left side, some portion or some span of the beam portion is overhanging from the any support that you have selected. Look at the diagram over here from support B. The span of that particular beam is extended upon some length, let's say length A. So over here we can say that this type of a beam having the hanging portion of beam, and it will be known as a overhanging beam. Generally, if such type of beam you are finding in which specifically one end is beam supported and other end is roller supported, at that time we can say that that will be only one roller support and one beam support. But it may not necessary that always right or even one-sided beam portion is overhanged. It may possible that in some particular overhanging beam, there are two-sided overhanging beam. Like that, the support is over here, and both of the side, left and right hand side, the portion of beam are overhanged. So if you are finding the overhanging beam in which the both of the sides of support uh, from which the beam portion are hanging, then both of the support that we are using in overhanging beams should be taken as a roller support. So in case of the overhanging beam, the single overhang, if a beam is single overhang, then pin and hinge and roller support like that is used. But if both of the side are overhanging, then the roller support must be used. So this is what about the overhanging beam. Then after fifth types of beam, and that is the fixed beam. It is the kind of modification is been taken from the cantilever beam, and modification is look like that. In case of cantilever beam, one end was fixed, but in case of fixed beam, if you are looking carefully, both of the and A and B both are fixed. And if you are looking such type of beam anywhere, then it will be a fixed beam. Look at the right hand side of figure. This is a one beam, wooden beam, and it is supported both of the end with fixed support. Due to fixation, it not allow any kind of horizontal and vertical movement, and also rotation too. So suppose you are applying force over here in horizontal direction. If you are applying force over horizontal direction over here, then the beam will not move. So we can say that the vertical or even horizontal movement uh, will not allow by this type of fixed beam. And also there will be nothing to rotation, because we know that both of the ends are fixed. So, due to the prevention of rotation, we can say that there will be nothing like the moment produced inside this type of fixed beam. One more thing, as compared to other previous types of beam that we have discussed, that majority of the beams are suffered with two primary categories. One is bending moment and other is shear stresses. But over here, fixed beam is only subjected with shearing stresses, because we know that there is nothing, any kind of moment, so there will be no moment of resistance, and that's why there is nothing like bending moment which produce in fixed beam. But yeah, of course, due to lateral forces acting over here, the section of this beam will subjected with shear stresses. So this is what about fixed beam, and generally used in truss and other similar kind of structure. Fixed beams used generally over there. Then after six types of beam that we are coming across, and that is propel or propelled cantilever beam. Look at the diagram. It is also the modification form of simple cantilever beam. In simple cantilever beam, one end is free and other end is fixed. But in case of propelled cantilever beam, other end is not free and it is supported by roller support. Uh, that is what about the propelled cantilever beam. And this type of propelled cantilever beam is always subjected with bending moment, or we can say that the bending stress and of course shear stress, because whenever you are applying force over here, it causes the bending moment over here. So that's why it creates bending stress. So we can say that this type of beam, propelled cantilever beam, is subjected with bending stress. And similarly, if you are applying forces on span of entire span of the beam, then this beam is subjected with shear stresses. So ultimately, as look the previous types of beam, this propelled cantilever beam is also subjected with both shear stress and bending moment. Then look at the screen. This is the third topic that we are going to discuss, and that is about the types of support. In previous topic, we have discussed about the types of beam, in which we have seen that different kinds of supports are being used. Either it may be the roller support, pin support, simple support, or fixed support. So it is necessary to discuss here the types of support and its characteristics. Look at the screen. First type of the support is roller support, and it is represented by symbolic form. Over here, it's triangle, and base of the triangle is represented by two circles. And if you are using roller support, as we have already discussed in previous, especially in simply supported beam, if you are using roller support, then it only allow the vertical horizontal movement, not vertical movement. So definitely reaction force will be acting in vertical direction. So we can say that the vertical reaction is possible in case of roller support, and resisting load, that is also in vertical direction. One more thing that we should to discuss over here is that suppose you are using any kind of support, then either it will offer vertical or horizontal movement, or horizontal and vertical reactions. Either it may be offer a vertical movement or clockwise movement and anti-clockwise movement. So how will you identify whether any kind of support which offer the reaction and the moment in particular direction? Well, this is very simple. Suppose you are using roller support, then we all know that if you are applying horizontal force on that particular beam which is supported by roller support, then it will be moving in horizontal forward direction. So it's clearly understand that it will not resist. So whenever there is nothing, any kind of resistance, it will not set up any kind of resistance force. So we can say that there will be nothing like horizontal reaction. But on the same roller support, if you are applying vertical force in downward or even upward direction, what happens? The roller support not move in vertical downward or upward direction. So it clearly means that it will offer resistance. So this is what the fundamental of the reaction calculation. Now, second and important, one more important support, and that is the pin support. It is represented by simple triangle, and if you are using pin support, then beam is pinned with particular support. And if you are using a horizontal force, applying a vertical force, so beam will not move in particular direction of that external forces. So both of the horizontal and vertical reaction may be set up if you are using pin support. Third category of support is fixed support. Uh, Suppose, as we have discussed in cantilever beam also, fixed support is permanently fixed with the wall or any kind of resting, like a wall or floor, whatever there is. And if you are using, if you are applying force in horizontal or vertical direction, once again, due to that particular force, your beam will not move in either direction. So it clearly means that horizontal and vertical reaction will be set up by this type of beam. And along with this, if you are applying force and force at some distance from the fixed end, uh, uh, over here at the fixed end, there is a moment. So ultimately, we can say that moment is also produced by this type of fixed support. And fourth and last support, types of support, that is the simply supported or simple support, which is generally used in simply supported beam. It's very clear from the figure or symbolic diagram that it will not offer any kind of horizontal resistance. So it may possible that by applying vertical force, beam will not move in downward direction. It will offer vertical resistance. So that's why vertical reaction force is set if you are using simply supported. So this is what about the types of different supports that are being used in different or various types of beam. Look at the bottom side, left hand side diagram, and this is a symbolic form. Also, pin support is there, roller support is there, and fixed support is there. Whereas right hand side figure is summary about what happens if you are using different types of support, and particular that support offers reaction and moment. Suppose hinge support is there, so it will offer a reaction in horizontal and vertical direction, and there will be nothing any kind of moment. If you are using roller support, then only vertical reaction is produced, that we have already discussed. There will be nothing like reaction in a horizontal direction, and a bending moment is also not set up. If you are using fixed support, then definitely it will offer a reaction in horizontal direction, vertical direction, and moment also. Then after we are going to discuss about the topic number 4, and that is the types of load. Dear friends, we have discussed different types of supports, different types of beams for which the load is acting. So herein it is very important to discuss the kind of loads which are acting on different types of the beam. And the first and most important type of load, that is the point load. Its name gives the meaning of that type of load. It is act specifically on point. So that's why name given point load. Look at the diagram. Over here, P force is generally point load or point force because it acts only on point contact or a point area. So that's why name given to such type of load is point load. It is also known as concentrated load too because it's concentrated at a specific area, and it acts on very small, or we can say that the acting area or length is very small for such type of point load. And unit of point load, either it should be the Newton or kilonewton. And for the moment or shear force calculation, all types of loads should be converted into point load. Either it may be the uniform distributed load, or it may be the uniform varying load, whatsoever. First of all, you require to convert all such loads into point load. That means this load. So this is what about the point load. Then second type of the beam, that is the UDL, that means uniform distributed load. It names gives the idea what is it, and the load which have the uniform intensity throughout the span of beam is generally known as a uniform distributed load. Look at the right hand side diagram. There is a beam AB, and over which there is look at this portion, for which the intensity of all bags are same at portion A to A dash, like that. So we can say that this portion of beam A to A dash is subjected with uniform intensity of loading. So if you are finding such a condition where the load acts on same or similar intensity of load is acting over the entire span of beam, then that will be known as a uniform distributed load. One more thing about uniform distributed load is that it is act through its center of gravity. Suppose over here, or even A to B, if you are taking this span, then intensity is definitely equal in A to A dash. But it concentrates center of gravity of the portion through which it acts, like that. So over here, it will act in downward direction. So it is assumed that if UDL is acting in particular or specific length, then it is act through its center of gravity. And what we have discussed in previous class, that the UDL should be converted into point load. But how? It's very simple. A point load is equal to UDL into span of UDL. That means suppose over here you require to convert this 1.5 kilonewton per meter of UDL into point load. Just you have to multiply with the 1.5 kilonewton per meter UDL with the span over which it is acts. That means 1.5 into 3. That means 4.5 kilonewton is point load. That is converted and acts through over here, acts through center of gravity of that particular span. So this is what about the uh, conversion of the UDL into point load. Be sure that UDL is converted definitely and must be converted to point load. But how? Just multiply the UDL magnitude, that means intensity of UDL, multiply it with the length or span of the beam over which it is at. So over here 1.5 into 3, it will be become the 4.5 kilonewton, that is equal to point load. But one thing is that where it should be placed, that 4.5 kilonewton you have definitely converted, but where it should be placed. So where it's very easy. Just you have to find the center of gravity of that particular span and put there. So over here, that will be your point load that you have converted from the uh, UDL. So over here, it will be F through center of gravity of that particular part. So this is what about uniform distributed load. Third types of the load that we are coming across, that is uniform varying load, means of UVL. Look at the diagram, left hand side diagram. There is a beam A, B, C, and D. That is section wise. If we are talking that section AB is subjected to some triangular types of load. Actually, it is a symbolic form of uniform varying load. Its name gives that the such type of load having the variation of intensity of load from one section to other sections. For example, over here, the intensity of that particular load is 0. If you are moving from A to B, there is a step by step or uniformly the intensity of that particular load is increasing. You can easily see from the figure of section AB. Over here, there is a 0 kilonewton per meter, but at the point B or section B, there is a 4 kilonewton per meter. So in that way, the load is going to be increased. And if you are finding such type of intensity of loading over any kind of beam, then that will be the uniform bearing and load. Generally, as that of what we have discussed in case of UDL, similarly, first of all, you have to convert this UVL into point load. And it's very easy to convert this UVL into point load. Just simply, you have to find out the area of the triangle, and it will be very easy. 1/2, that means 1 into 2 multiply with, that is the height, that is 4, and that is the base, that is x. So if you are doing so, that means if you are calculating area of that particular UVL, you will have the conversion of UVL to point load. Look at the screen. Just I have multiplied with 1/2 into W into L. Over here, W is the intensity of UVL. That is, you can consider it as a base, and L, that is the span over here. That means this span AB. Consider it is a length or L. So if you are multiplying, so you will have the conversion from UVL to point load. Then once you have converted point load from UVL, then the question arises that where it should be placed. In case of UDL, we have placed this point load in midway, that means center of gravity. But over here there is a triangular load, so you are not supposed to put that point load in center of that particular triangle. It's not look so. So first of all, you have to calculate the point load, and once you are you have calculated point load, you just put the exact location of that particular point load. Look at the right hand side diagram. It's very easy. Just you have to find the center of gravity of that particular triangle. Suppose CG of that particular triangle is over here. So this over this or through this center of gravity, the whatever the point load you have converted will act in particular direction. So first of all, find out the a point load from the UL and put that point load on CG of that particular triangle. And now we all know that CG of triangular is located of 2/3 into length of that particular triangular on left hand side, or 1/3 means this. This is the 1/3 of total length of triangular. You can put from any sides. If you are taking left hand side, you should to take care of 2/3 length. If you are taking right hand side, you should to take about 1/3 of total length. So this is what about the uniform bearing load. Now we are coming across the point number 5, and that is a few examples that we are going to solve based on the previous theories we have discussed. Look at the screen. You have given one simply supported beam which is 6 meter long and carrying uniform distributed load of 5 kilonewton per meter over a specific length of 3 meter. That means between C to B. That means over here C to B, the UDL is acting having the 5 kilonewton per meter. Just you require to draw the shear force and bending moment diagram for the beam, and also calculate the maximum bending moment which is acting in either A, C or B section. So this is what example says, and let's have the solution. First of all, just you have to, before calculating shear force and bending moment, you require to calculate the lateral forces. That means the forces which are acting in vertical direction. So over here, there is a 5 kilonewton per meter, that is UDL, which is definitely acting in downward direction. But what happens at the support A and support B? Because force 5 kilonewton 5 kilonewton per meter UDL acts, so definitely both of the support A and support B will offer a reaction force in vertical direction. So first step of your calculation should be start with the calculation of the reaction at the both of the supports, and it's very easy. Look at just you have to take moment on either support A or B. Over here, by taking moment about point for support A. That means over here, just you require to have the moment, and it's very easy to calculate. Sorry, there is a little bit mistake from my side. In this particular moment calculation, the moment is taken about the fixed support A over here. So just around and about point A, moment should be equated in clockwise direction and anti-clockwise directions. RB into 6, that is the moment, because RB is acting upward direction and perpendicular distance of that RB to A is 3 plus 3, that means 6. So RB into 6, that is the moment, and which is acting in anti-clockwise direction about support A. So that will be anti-clockwise direction moment will be taken as a left hand side. It should be equated with the clockwise moment which is offered by that particular UDL. And first of all, just you need to convert this UDL into point load. So over here, UDL into the portion or the span over which UDL is act. So over here, 5 into 3, that will be become point load from the UDL, and which is exactly acting through the CG of that particular span over which the UDL is acting. That we have already discussed in case of UDL law. So that means 5 into 3, that means 15 kilonewton, that is the point load which we have converted from the UDL and which is act and the CG of the particular span. So 15 multiply with the distance uh, uh, up to A, that is equal to 3 plus 1.5. So ultimately the distance is equal to 4.5, and force into perpendicular distance which offers the bending moment or simple moment at point A in clockwise direction. So this will be the clockwise direction. So over here, first step is to just you have to equate the moment which is acting in clockwise direction and anti-clockwise direction. From that moment, equating moment, you are finding first reaction at support B, and once you have the reaction at support B, you will easily calculate reaction at support A. Now, once you have calculated A and B reaction, it's time to discuss or to calculate about the shear force which is acting on different sections. Section A, section C, and section B. So, starting with the section A, it's very easy to calculate. Look at the section A over here. Uh, Over section A, there is only one force, that is the RA. That means that is equal to 3.75 kilonewton, which is acting in upward direction. So it will be taken as a positive 3.75 kilonewton. Similarly, if you are looking for the section C, then above and around section C, there is only one force that is acting, that is 3.5 kilonewton, because this force can be easily transferred over here as per the engineering mechanics. So whatever the section you are considering, just you have to think about that particular section and left hand side of that particular section. Suppose over here we are calculating the shear force at section C, then just think about this portion only and think which kind of force is acting in which direction. So over here only one force is acting, that is 3.75 kilonewton, nothing other than that 3.75. So it is also acting in upward direction. So sign convention for the simply supported beam is like that. If force is acting in upward direction, you should to take it as a positive. If force is acting in upward direction. So over here we have taken 3.75 kilonewton in upward direction. So this is what about. So this is how we can have the calculation of shear force at point C. Now think about the shear forces which are acting at point B. Think the portion B or section B and left hand side of that particular B. So over here, entire span is covered, and one force is acting in upward direction, and other force is acting in downward direction. So this should be taken as a positive, and as per the sign convention of simply supported beam, this should be taken as a negative. So over here 3.75, and this is UDL, so you need to convert this UDL into point load, so 5 into 3, but it should be taken as a minus because acting in downward direction. So 3.75 minus 15 is equal to 11.25 kilonewton, that is the force which is acting in downward direction. Now, once you have calculated the shear force which are acting in different sections, uh, Then you just calculate the bending moment at that particular section. Starting from the section A, that is or the left hand side support. Uh, uh, we all know that the moment required to have the force and perpendicular distance. So if you are calculating moment at point A, then think about what I said earlier. You just to focus upon that section and left hand side of that particular section. Over here, exactly, there is a force which is acting on section A, but there is nothing perpendicular distance with that particular section A. So force 3.75 into distance, that will be equal to 0. So ultimately, we can say that the bending moment at section A is equal to 0. Now, similar procedure you have to adopt for section C. Suppose you are calculating bending moment at section C, then think about the C and left hand side of it. Yes, there is a one force, that is 3.75, which is acting on left hand side of the section A, span AC, and there is also perpendicular distance is available 3 meter from this section C to section A. So we can multiply 3.75 perpendicular distance 3 meter, so 3.75 into 3, and that is equal to 11.25. That is the moment which is acting in clockwise direction over section C. Uh, as what we have discussed, sign convention for lateral or shear force, that is, if a force is acting in upward direction, you should to take it as a positive, and if acting in downward, it should be taken as a negative. Similar sign convention you should to follow. Suppose the bending moment is acting in clockwise direction, you have to take it as a positive. Be sure about that sign convention for bending moment. And suppose you are finding that there is a simply supported beam and moment is acting in clockwise direction, you should take it as a negative. So over here at the section C, the bending moment acts in clockwise direction, that's why it is taken as a positive. Similarly, if you are finding the you are calculating bending moment at section B, then you have to focus upon above section B and left hand side of section B. Basically, no need to calculate such type of calculation of a force into a perpendicular distance, force into perpendicular distance, because in simply supported beam, both of the ends where the moment is equal to 0, because in theory whenever I have taken simply supported beam, at that time I clearly mentioned that it's because of simply supported, it will not offer any kind of moment. So moment in simply supported support or simply supported beam at both of the end will be always 0. But however, or you may also check by calculating the same bending moment at point or section B, like that. So 3.75 into 6, that is clockwise direction, so it will be taken as a positive, and 5 into 3, that means over here, that is the 15 kilonewton into perpendicular distance, which is acting in anti-clockwise direction. So clockwise and anti-clockwise, both of the values should be put over here. Ultimately, you will find that there is a 0 kilonewton into meter. So this is what about the bending moment calculation. Now, once you are calculating shear force and bending moment, you need to draw shear force and bending moment diagram. That means SF and BM diagram. It's very easy to draw. First of all, you have to draw a vertical dotted line from each and every section like that. And then just think about the each and every sections. Suppose first of all you are drawing this shear force diagram. This is shear force diagram, this is bending moment diagram. So we should start with the drawing of shear force diagram. This is shear force diagram. So first of all, before drawing that shear force diagram, just draw a horizontal line like that, and draw a vertical dotted line from each and every section like that. Now, take some suitable scale by looking the magnitude of force over each and every section that you have calculated. A, C, and B, out of that three section, maximum amount of force or shear force that is acting at 11.25 at point or section B. So you should to select scale in accordance with that magnitude. And once you are selecting that 1 centimeter should be taken as a 2 kilonewton or 5 kilonewton as per your space available in graph or say in your examination paper, you can take a suitable scale. Once you are calculating or once you have decided the scale and according to that particular scale, you need to draw a simple diagram, that is shear force diagram. First of all, starting with the section A, we know that at section A there is a 3.75 kilonewton force is acting in upward direction, and it will be taken as a positive. So positive will be always in upward direction to horizontal line, and negative will be always in downward direction to that particular horizontal line that we have drawn earlier. So 3 kilonewton scale wise, you should to put or first of all, suppose you have taken the 1 centimeter is equal to for example 3 kilonewton. So at point A, you should to move 3 centimeter in upward direction. Look at that particular point, 3.75, where it is coming. Similarly, at point C, there is a 3.75 kilonewton. So same theory or same procedure you have to adopt, move in upward direction as per the scale, and it should be over here 3.75 centimeter should be marked over here. And at point B, there is a 11.25 kilonewton is acting, but it is acting in downward direction because sign convention of that shear force which is acting at point B is minus. So from that particular point or section B, you should move at 11 centimeter exactly below that particular horizontal line, exactly 11.25 centimeter, and put or mark over here, that is your the 11.25 shear force which is acting at section B. Once you are located all the points A, B, and C, then you have to think about the types of load which are acting in between both of the sections. Over here, section A and section C, both of the sections, there is a shear force acting. We can say that it will be joined with the horizontal line. But between C to B, there is a uniform distributed load. So if uh, any two sections in which the UDL is acting, shear force should be connected with an inclined line. Similarly, if any two sections are there, section A and section C, and there is a shear force load or shear force acting, or if there is nothing, there is no any kind of load is acting, then consider or connect both of the points in horizontal line. So this is what the shear force diagram that we have discussed. Now, after shear force diagram, we should to draw a bending moment diagram, and this is the bending moment diagram. Uh, uh, Similarly, as that of shear force diagram, you have to extend that sectional line to horizontal line drawn for the bending moment diagram. So all the lines should be extended over here, and one by one, as we have already taken scale, that is, for example, 1 centimeter is equal to 1 kilonewton in case of shear force. Similarly, you can select the same scale, or you may also suppose there is a large or amount of bending moment, you can select as per your convenience and available space for the bending moment diagram. So by considering that we are selecting the same scale as that of the shear force diagram, and we are drawing bending moment diagram, then first of all you need to locate all the points or the moment which are acting on different sections. So we know that at section A and section B there is nothing, zero bending moment, so it will be marked horizontally. But section C, where the bending moment acting in clockwise direction having 11.25 kilonewton into meter, that is the value for bending moment at section C. So just you have to move in 11.25 centimeter, because we have selected 1 centimeter is equal to 1 kilonewton into meter. So 11.25 centimeter if you are finding from that particular horizontal line, then mark that particular point, that will indicate 11.25 kilonewton into meter bending moment acting over there. Now it's time to have the joining of all that particular points. In case of while you are drawing bending moment diagram and there is there is no point load or even point load is acting between two section A and C, or say any two section, then both of the sections should be joined with an inclined line like that. Similarly, while you are drawing bending moment diagram and if two section in which the UDL is acting like that, then both of the sections should be joined with a hyperbola, or we can say the simple curvature line. Okay, by joining that, you have the bending moment diagram. So this is what the first answer we have calculated and drawn shear force and bending moment diagram. Now we need to calculate maximum bending moment. It's very easy to calculate maximum bending moment. Just you need to focus upon this section. There are basically two triangles, so simple ratio has been taken. This is the point of contraflexure. It is simply crossing the horizontal line, or we can say that it is the point through which the sign convention from positive to negative is going to be changed. So ultimately, just you need to focus this two triangle, and ratio has been taken uh, from section C to point M. It is let it is the distance x that we have assumed, and now ratio is look like that. Base of one triangle upon the height of the triangular is equal to base of other triangle. That means entire length is 3, and it should be subtract from this distance x. So ultimately this will be 3 minus x. So we can say that this triangle has base 3 minus x, and which is divided by the magnitude, or we can say that the height of triangle, that is 11.25. So by equating both of the ratio of triangle and simplifying it, ultimately you are finding the distance of x. And now, as we know that bending moment has the higher magnitude when shear force is 0. If you are finding any section in simply supported beam where the shear force is 0, we can conclude that the bending moment is acting highest out of all the remaining section over their particular simply supported beam. So over here we have find a section that is the section M, which is located at 0.75 meter from the section C, where the shear force is equal to 0. So we can conclude that this section M contains the maximum bending moment. So you require to just calculate the bending moment at section M. And in a similar way, what we have calculated the bending moment in all the section. In similar way, you have to just calculate the bending moment over section M. So left hand side, just you have to taken care of. Look at the section M, and left hand side of it, the forces and the distance should be multiplied with it over here 3.75. That is the force acting over here, and the distance should be taken up to this. Okay, so this will be the distance will be 3 plus over here x is equal to 0.75. So ultimately it will become 3.75 into 3.75. That will be the distance and force. Along with this, there is one also force that is acting over here, that is UDL, because we know that we should to take care of only this support, this section, this length, this span, and over this span there is 5 kilonewton per meter UDL is also acting. So just you need to convert first this UDL, which is acting on that particular 0.75 meter into point load. So it will be uh, uh, 5 into we can say that 0.75 divided by 2. And by converting this point load from this small portion and multiply with that particular distance, you will have the bending moment due to that particular UDL. So by using that relation, you are finding that the bending moment acting over section M is equal to 12.66 kilonewton into meter. So this is what about the shear force and bending moment calculation. Also, we have drawn a shear force and bending moment also, and at the end, we have calculated the maximum bending moment which is acting at the section M. Dear student, this lecture is very much important not only for this subject because this contains some design concept also which will be used for your higher semester subjects like motion design and theory of motion and kinematic of machinery too. Enter this lecture, we have covered an introduction of beam, types of beams, then types of load, and also types of support. At the end, we have also solved an example in which we have specifically calculated shear force and bending moment. We have also draw shear force and bending moment diagram and also calculate maximum bending moment which is acting at any section of that particular field. I hope that you are getting well this my video lecture. You boost up your knowledge regarding these subjects. Kindly stay tuned with us, and if you are finding any difficulty, let me inform. We will discuss in depth, and we have the better solution for your query. Once again, thank you very much.